Hello everyone, we will be talking about chapter 5.6 and 5.7, equations of equilibrium and constraints and statical determinacy. So we have already discussed equations of equilibrium in two-dimensional problems. We're summing our forces and we're summing our moments. When we add the third dimension, now we're going to have our sum of our forces in the z, and then we'll be discussing how, if you're looking at the I, the J, and the K, and how they are independent from each other, you will actually have 6 equations, and we'll be discussing that here in a little bit. We'll also be discussing constraints and statical determinacy. So on my page here, I have the exact same pictures that you have. These are actually from chapter 5.5, free body diagrams in 3 dimensions. So let's go through them. You also have them in your book, but let's go through them kind of quickly. We have a cable, and if you notice, the cable is shown with one force. A smooth surface support, meaning that it's allowed to slide but not allowed to go up and down, has a reaction force. A roller is the same as a smooth surface. We also have the force reaction which acts perpendicular to the surface. So the next slide, if you have a ball and socket, note how it's allowing it to rotate, so there are no moments on here, but it does not allow it to move in the X, the Y, or the Z. Therefore we have our reaction forces in those points. Now if you look at a single journal bearing, now it is allowing it to slide, so we have no reaction forces going this way, but it is not allowing it to move up or rotate here, or it is not allowed to move in the X direction, if we call this our X, or rotate along that axis as well. So we have reaction forces X and Z, and we have moments X and Z, but we have no reaction force or we have no moment along our Y. So just note that these are, because it is holding it in place, it is in static due to those. Single journal bearing with a square shaft. Now note that in the Y direction it is allowing it to move, but it is not allowing it to rotate. So if you notice, there's no force in the Y. It's showing a vector here, but it is not allowing it to rotate because it's square. A single thrust bearing, now it is not allowing it to move in the Y direction now, so you do have a force in the Y, but it is allowing it to rotate, so there is no moment holding it there. So you kind of get the gist. We have a single smooth pin, and we have our last ones, which would be a door hinge. If you notice, it does not allow it to rotate in the X or in the Z, and it's not allowing it to move in the X, Y, or Z. And then a fixed support is not allowing it to move anywhere or rotate in any direction. Therefore we have all of our 6 unknowns. And just some examples: you have a ball and socket, and this provides a connection for a housing on an earth grader to its frame. You have journal bearings, support the ends of the shaft. You have a thrust bearing that is used to support the drive shaft on the machine. So you can kind of start seeing where these reaction forces are helping these real live scenarios. And then the pin is used to support the end of the strut used on a tractor. Okay, so I'm going to slide down here, and we're going to look at statical determinacy. And when you think about statical determinacy, and you look at this one here, so we've got a beam, and if this beam is subjected to a load P, and we note that there are 2 rollers, what's going to happen to this beam? Exactly, it is going to move because there is nothing holding this beam in the X direction. So this is statically indeterminate. We could not solve this problem because it is going to move on us. Yes, people will say, well, there's friction and all that, but this force is going to move the beam. Therefore, you're getting into dynamics, and we're not going to be doing that here. So this would be statically indeterminate for us. So let's say we have a pipe or some kind of light fixture hanging from the ceiling, and we have a force pushing on this. Again, this would move. We only have forces in the y, nothing holding it in the x, therefore it would move on us again. And here, this is a pretty interesting problem. We have two fixed joints. If we have two fixed joints, now we have, if we're just breaking it up and we're looking at from A to B, if we're just taking that, we'd have a force in the A, a force in the B. If we summed our forces in the x, we have two unknowns. Therefore, we would not be able to solve for these forces. Or if this was one long beam without these pins, you could say I'd have a reaction force at A, a reaction force at B. Therefore, we could not solve this since we have two unknowns and we don't have enough equations to solve for those problems. Remember, you'd have to have two equations, two unknowns, three equations, three unknowns, and in some of our 3D problems we'll have 6 equations and 6 unknowns, so we'll be able to solve for everything. So back to what I was originally talking about, we have our equilibrium equations. And with our equilibrium equations, we have our sum of our forces is 0 and sum of our moments are equal to 0 at some point. So if you look at our scalar equations, we have sum of our forces, which is my sum of my forces in the x plus the sum of my forces in the y plus my sum of my forces in the z are all equal to 0. And we have my sum of my moment is equal to my moment about the x, my moment about the j or the y, and my moment about the z is all equal to 0. So you note that I, j, and k are all independent of each other. Independent of each other. Therefore, you have your sum of your forces of the x is 0, your sum of your forces in the y is 0, your sum of your forces in the z is 0, and you have your sum of your moment of the x is 0, sum of your moment about the y is 0, and your sum of your moment about z is 0. So therefore, all of these are true due to the fact that you have all of these, they're independent from each other, so you're going to have all 6 equations. So let's do a few examples on the next couple of videos to help you understand the reaction forces that we're looking at. If you have any questions, please post them on the discussion board so we can take a look at them.